All right, I am back. We are going to continue on with the introduction to analysis of variance. We just covered t-test. And so far what we've done is we've kind of looked at how to compare the following. We've learned to compare a sample to sample, the independent t-test. We're going to do a sample to a paired sample with a dependent t-test. But what happens if we have more than 3 samples? That happens a lot, right? Traditional memory technique, new memory technique, no memory technique. Condition 1, 2, 3. Going back to that example from the previous lecture, what we want to do, control group, cognitive behavioral therapy, art and music therapy, and another type of therapy, traditional therapy. How do you make those comparisons? All of these things relate to one independent variable. In the example right here, let me get my pointer. In the example right here, it's a memory technique, right? In the example previously from the previous lecture, it was a therapy technique. That is one independent variable that has either 1, 2, 3, 4, or however many levels that exist. And so how do you do that? Well, you could compare in the above here, condition 1 to condition 2, condition 1 to condition 3, condition 2 to condition 3, using t-tests. So you could do 3 t-tests to analyze these variables or these levels. However, that is not an efficient way to do that. Not only is it not efficient, it creates potential error. The problem with doing that, it's inefficient. We have to calculate 3 tests. Imagine if you add one more group, you are exponentially adding things that you need to make comparisons for. It's also unnecessarily and theoretically, it introduces error into our statistical test. And this is something called family-wise error. Family-wise error is where within a group of analyses that you're doing, every time you do another analysis, you get closer and closer to the theoretical existence of a false result. Because the more things you do, the more likely you are to hit that point where you're like, okay, well, if it's a 1 out of 100 chance, if I do enough analyses, I'm going to hit that 1 out of 100. And so you try to keep that family-wise error down. We can use something called an analysis of variance. This is something that is more formally or informally called an F-test. And the Anova test can be used to test the difference between 2 or more means. It's actually very similar to a t-test, except it allows you to do 3 levels or 4 levels or 5 levels and so on. If you were to compare a t-test to an Anova, you would find that after going through the same procedures we use for a t-test, calculate the statistic, use the degrees of freedom, find the statistical values, the resulting probability that you obtain would be identical to the probability using a t-test because they're the same test. They're based on the same logic of comparing one independent variable across multiple levels of that independent variable. In fact, when you look at it, F itself is equal to t squared. So if you have a 2-level ANOVA, or 2-level one-way ANOVA, so 2 levels, one independent variable, and you compare that to a t-test, if you square your t value, you'll get your F. They're exactly related to one another. So let's look at an example. Say you're looking at a new drug treating migraine headaches, and you look at 3 groups. They're randomly selected. The first group receives 250 milligrams of the drug. The second group receives 100 milligrams. And the third group receives the placebo group. So you have 3 groups, and you'll see that there's a low value here, a medium value here, and a higher value here. And you want to see which one reduced the amount of pain on a 0 to 20 scale. You can see it looks like there's differences, but are they statistically significant differences? That's the question, right? Not only whether the differences appear to be there, but whether they're actually statistically significant. You could do t-tests. You could compare 1 to 2, 1 to 3, and 2 to 3 to determine this out. A more efficient way is to do an F-test and look at these as a whole to figure out whether there's a difference. And that's what we're going to do in a one-way analysis of variance, a one-way ANOVA. If we were to calculate the ANOVA, we could report the results in a couple of different ways. Method 1, by saying it, by just writing a sentence. The difference between the means was statistically significant. At the 0.05 level, we have our F, which is our statistically calculated. and we have degrees of freedom. We're going to have 2 degrees of freedom in this situation as opposed to 1 value. This method is similar to how we report our results of a t-test. And in this case, the null hypothesis for this example states that the set of 3 differences was created by chance. If we reject that null hypothesis, we're assuming that there is a statistical difference between those groups. We then have to go figure out where those differences are, but currently we are just looking at whether there's an overall difference. This does not tell us where those differences exist. We don't know which ones are responsible for the rejection. Is it, going back to our values, is this value different from this value? Is 1.78 different from 3.98? Is 1.78 different from 1288? Is 3.98 different from that? Which one is those is different? Method 2 is to report ANOVA using an ANOVA table. And we've already looked at ANOVA tables when we did regression analyses. Those regression analyses contained an ANOVA table as part of those results. It has sums of squares, degrees of freedom, and so on. This here is what, and I just lost my, I'm going to pause the recording because my PowerPoint just shut down. Sorry about that. So we got our ANOVA table. One of the ways is to put this into an ANOVA table. You have the source of variation, so where there's differences. You have your degrees of freedom, sums of squares, mean squares, and your F. This is the important one, the F, and the degrees of freedom. The stuff in the middle is only important if you're calculating this stuff by hand, which you're not. Degrees of freedom, in the first group, it's the between is the number of groups you have minus 1. So in our example here, we have 3 groups minus 1, degrees of freedom of 2 for that between. In the example with our therapies, if there's 4 groups, it's 4 minus 1, which would be 3, okay? Within degrees of freedom, you take away 1 for each group. So there's 3 groups, you minus 1, 2, 3. Okay, so that's 3, and that gets us down to 36 because there's 13 people in each of the groups. And then the total degrees of freedom is your big N, which is the total number of participants, minus 1. So when we look at the ANOVA table, the between groups variation. So what does that mean? The between groups variation is where the differences exist between each of the groups as a whole. So you're looking at group here, you're looking at group B here, and you're looking at group here. There is differences potentially between, I'm using my finger like that helps, between each of these groups. So the group column 1A, it has a mean of 6. The group of column B has a mean of 5.5, and C is 2.33. Each of these groups differ from each other as a whole. That's between groups variation, right? The difference between those. Now, within groups variation relates to the fact that within any group in and of itself, there is variability. The score 7 is not the same as score 6, which is not the same as score 5 or 8 or 3. 7 is the same, but it's still variability. And so there are both types of variability that we're looking at. That's why it's called an analysis of variance. The variance exists on multiple levels, either between groups, between group A, B, and C as a whole, which you can get from looking at the sum of the values or the means. Those are different. And then within each group, there's also variability. And it's the same for each group, right? The variability within each group is within group variability. You also have total variability, which is if you just take everybody as an individual and look at how they differ from each other, there is variability that exists. Once you compare all of these variabilities, you can determine whether the difference between groups, whether the difference here, the means, is greater than what would be expected based on the differences within the group or as all the group as a total. So that's essentially what you're doing. You're taking variability and you're breaking it down into all its constituent parts. You know, within, I'm going to do this one more time, as groups within each group and then as a total, and you're saying, okay, where's my variability, and is that variability enough to suggest that yes, group A is different than group B and group C, and not just within group variability or not just total variability that exists. So is another, well, I don't want to actually cover that example. I'll let you guys look at that. So what we've been studying, what we've just looked at is something that we're going to classify as one-way ANOVAs. They're single factor ANOVAs. So these come from the fact that participants are being classified according to one way. In our first example, they're classified according to the drug group in which they were assigned. In this second group, it's literacy, computer literacy, right? In the example that I gave in the previous lecture, it was type of therapy. Those is one way in which the group is classified. That's why it's a one-way ANOVA. We're also going to learn about it down the road about two-way ANOVAs and repeated measures ANOVAs. Two-way ANOVAs have more than one independent variable. They have multiple independent variables, 2, sometimes 3. Then it'll be a three-way ANOVA or 4. And then repeated measures ANOVA, where you are testing the same group over multiple points in time. So I might do a therapy group where they're getting the control group, they're getting the art and therapy sessions, they're getting the cognitive behavioral therapies. And so they're looking at all three of those to see which one is actually functioning and working better for that client. This is what the data looks like. We're going to go over this in class a little bit more, but I've highlighted the important things. These are the means that exist. These are the ends. This is your ANOVA table right here, right? Your F is important, your significance value is important, and your degrees of freedom is important. And then you're going to have to do a multiple comparison procedure. All this F tells you is, hey, there is a difference somewhere between those three means. Right here, there's a difference. Where is it? I don't know yet. So you run a multiple comparison procedure, usually a Tukey or a Chaffee's test, and it then goes and runs all the comparisons between those groups. If this value is not significant, you stop right there. And you say, okay, there's no difference, I'm not going to look. That maintains your family-wise error. If this is significant, you then go in and say, oh, I'm going to make comparisons now between group 1 and group 2, between 1 and group 3, 2 and 1, 2 and 3, and then 3 and 1 and 3 and 2. That assesses all the variability that might exist between those groups. And you're looking at these significance values. If they're significant, it says, yes, there is a difference between group 1 and group 2. Yes, there is a difference between group 1 and group 3. And that is coming from these significance values. And you would report those the same way you do like a t-test. There are some rules with Tukeys and Chaffees, but I want to cover those in person when we're together. All right, so how do you use SPSS to compute t-tests and one-way ANOVAs? That's what we're going to cover next. Before I do that, apparently, I'm going to jump into writing up your statistical results. I forgot I did that. For all statistical writing, you should be aware of the following. You're going to provide the test value, the degrees of freedom, and your p-value. That's the standard model that you're always going to use, right? Test value, it's the t. Degrees of freedom is 21. The value of the statistic is 2.56, and then you give your p-value. You're going to provide the means and the standard deviations. If they exist, you provide them, because this is what's going to help you determine if there's differences. And then be specific to the question that you originally asked. This is really important, right? Responses that are generic, group A differed from group B, not acceptable. You have to be specific. So you would say, if this was a statistically significant result, results demonstrate that men with a mean of this and a standard deviation of that were significantly different from women, mean of this, standard deviation of that, and then you would report that t-value here. And then you're going to follow the APA formatting when reporting statistics. You're going to use italics, you're going to use statistic abbreviations, you're going to do those kinds of things. This kind of talks about the same thing when you're talking about t-tests, regardless of whether they're independent or dependent. Once you get to the end, you're going to have the same information. You're going to report means, you're going to report standard deviations, you're going to report the t-test, including the standard degrees of freedom and p-values. And so at the end, you're going to come up with a written sentence that looks like this. You say an independent or dependent t-test indicated that the difference between the means was statistically significant. You report the t-value, including the degrees of freedom, the value itself, the p-value, and then you say specifically, and then you list the group. Don't say group A, men, and then you provide the values for men, was significantly bigger or smaller than group B, and then you're going to provide the values for that. And then you're going to interpret. This is the interpretation part. This suggests that you provide some sort of concluding statement, that there is a significant difference between men and women on this item. Running SPSS, you're going to click on Analyze, and then you're going to move to Independent Samples T-Test. You're going to have to define your groups. That's a key part of this process. By defining your groups, you're going to enter in your independent variable and your grouping variable. So gender is the variable I'm looking at. You're going to define groups. It's going to open up this thing. You're just going to say what numbers were assigned to those groups. And then you're going to put in your test variable, and you can put as many of them as you want. You also can do the same thing for a dependent t-test. It's going to look something like this, where you're adding them into this line here. And this is the data you get, right? You're going to get means. You're going to get standard deviations. You're going to get t-values. You're going to get significance values, okay? You're also going to get something called the Levene's test of equality for variances. In this situation, this tests whether your degrees of your standard deviations are significant enough, or whether they're similar enough. If the variability is too different, you should actually use the equal variances not assumed line. So this line here, you'll see it's slightly different than the other one. There's some theory behind it, but it just does a slightly different statistic. And so if this is significant, then you will use this one or this one based on that value. This is not significant, so you use equal variance as assumed, and your t-value will now be 7.95, degrees of freedom is 25, and your significance values of that. Same thing with dependent t-test, except here you're going to look at the end over here where your t-values are. T, degrees of freedom, significance values. Don't worry about the correlations, and then your means are always important. Always important to look at the means. That stuff is highlighted in your statistics write-up cheat sheet. That will help you in learning how to interpret that data. That's important. That's important. That's important. Then we have this is important, and this is important. Everything else you can kind of ignore. It does have relevance in certain situations, but not for what you guys are doing. One-way ANOVA, you're going to look at the means, you're going to look at the standard deviations, and you're going to include the F, including degrees of freedom, and the p-value. And again, you can just write this up. You're going to write it up by saying the one-way ANOVA found a significant F test. Then you provide the F value, you provide the p-values, and this suggests that there is a difference among the three groups. And then you're going to look at the two keys test or the Chaffee's test, whichever one we talk about doing. And then that will tell you how your groups differ. And then you're going to write down those values. You're going to tell me where specifically those differences exist. Again, when you're running analysis variance using SPSS, it's a one-way ANOVA. You're going to put your factor in here, which is your independent variable. You're going to put your dependent list, so which variables you're looking at. You're going to look at options. You can define some of those, and then you're going to pick your post hoc test. Like I said, usually you use two keys or Chaffee's. Those are the two key ones that we use. And we can talk more about that in class. This is what your values look like. This is one where it's not significant down here. So this is your means of all your groups, group 1, 2, and 3. Your mean, I think I have there. So your means, your standard deviations. Those are important. And then here's where you're looking at your degrees of freedom, your F, and your significance values. The F is this. It's 2 and 24. It's 1.67. Your P is 0.210. This is not significant. So we stop. We don't even look at the tables down here because it's not significant. This one is significant, right? 2 and 13 is significant. Or 2 and F of 2 and 13 is 76.417. 42 if you round. Your p-values of that. This is significant, so you can say this ANOVA is significant. So then we look at our values here and we see where the differences are. It's showing that there's differences among all of the means. Every one of the means is different from all the other ones. All right, so that is how you do an ANOVA and how you do a t-test. That was a very quick version of it. We're going to do this in class on our lab 2. And so be prepared to do that this next class period. Look over this stuff, look through the things, be familiar with each of the tests, familiar in the sense that when I talk about t-tests, you know what I'm talking about. When I'm talking about ANOVAs, you know what I'm talking about. And then we will do the analyses themselves next week together in the lab together. So that is all I have for today. We had a Zoom class tonight. Great class. And I think that's it. All right. Have a good day.